Yes, I'm going to talk about, I think on the title of the slide, it says I'm going to mention Bandung. Unfortunately, I'm not going to mention Bandung because I've got a bit too much to say about Hanoi. So we'll focus on that. But this is essentially a talk about subsidence in Hanoi. And there's been a lot of studies done in Hanoi over the past. We've had a project there for the last 4 years within our Overseas Development Assistance program to look at urban development, urban hazards within Southeast Asia, and Hanoi has been the focus of some of that. But there's been a lot of studies on subsidence in Hanoi, and a lot of those studies have linked it to groundwater abstraction. And we've been looking at the data, and I'm just kind of questioning whether that's the only process in play within there. So I'm just going to show you some of the ideas that we've got. So Hanoi is in northern Vietnam. It's it's on the Red River Delta Plain. You can see here on the map where it is. Hopefully you all know whereabouts in the world we're talking about, Southeast Asia. The important thing about Hanoi is the Red River Delta Plain, and you can see actually in this DEM image up at the top that we're sitting on an area of kind of this classic triangular looking area of lowland where we've got these soft squashy sediments of the Red River Delta. The other important thing is the rapid urban development. There's been a nearly 16% increase in artificial surfaces over the last 50 years, and the population of Hanoi is rapidly increasing. And because of this population increase, the government have been putting together a master plan to help guide the development of the city and trying to focus that development into kind of satellite towns around the centre of Hanoi. And I just found this graphic here, which I thought was quite interesting because you can see there's a decrease, they're planning for a decrease in agricultural land and an increase in kind of urban land, so industrial land for housing, land for public services, etc. And that's putting pressure on resources such as groundwater. So there's an over-extraction of groundwater, which several studies have found leads to subsidence. But it's also putting a pressure on things like material flow. So where's the raw materials coming to build this, these new buildings and these new roads, which is something else that we've been looking at. So as part of all of this study, we've created a 3D model using the same software that Hannah was talking about earlier on. So that was a great introduction. And this has been put together from borehole data. And the borehole data wasn't quite as rich as we would like, but the overall important thing to take from this slide is that there's an increase in clay content to the southwest of the city. So this is the Red River here marked in white, and the city centre is essentially here. And we're just going to be looking at some areas around the city centre, around here. So you can see from the kind of the grey colour in these cross sections that there's an increase in clay, and it's thicker towards the southwest. So we've been looking at INSAR data. We've processed some INSAR data from both persistent scatter interferometry and also small baseline and subset interferometry. I don't want to go into the technical details of INSAR. Hopefully most of you are pretty familiar with it, but I just put the classic kind of picture down at the bottom here, just to highlight that we're looking at millimetric precision motion, which has been derived from satellite radar measurements. You're looking at the difference in the phase. So it's a physical characteristic of the radar measurement, that's the radar wave that's reflected from the Earth's surface, and so you're very precise in what you can measure. And you're looking at that over subsequent images. So we've got several hundred images processed over the last 5 years. And this gives you a map like you're seeing here in the top right corner, where the red areas are kind of subsiding and the green areas are stable. What's interesting is that the centre of Hanoi here is now pretty stable, whereas it's these areas around the south and the southwest which are undergoing motion. So when we started looking at this data, one of the first things that we did was started reading the literature and seeing what the people had done. So this is just an image taken from a paper by Dang et al. In 2014, where they were looking at ALOS data. So we were using Sentinel data, which is C-band, about a 5.6 centimetre wavelength. This is ALOS data, so it's a different wavelength, a bit longer. But it's giving you the same information. What they found within their study were these areas of subsidence. You can see them with these purple boxes around them. And these areas of subsidence were linked to boreholes, Q64, Q65, and Q69, all of which, there we go. I was hoping I had those circles. I was a bit worried I didn't have them. So these highlight where the boreholes are. So you can see that these boreholes are sitting over these areas of subsidence. And And we're seeing quite, high rates of subsidence related to groundwater abstraction. However, if we now look at the INSAR data that we've processed, so the more recent data, the previous data was 2007 to 2011. The data that's now on the screen is 2015 until 2021, early 2021. We can see there's a difference in the patterns of motion, and also some of the areas that were subsiding, so certainly around Q64 here, this borehole, is now stable. And the subsidence around Q69 has kind of migrated to the south of the borehole. So it's not directly related to the borehole as it was. Well, the spatial relationship isn't as obvious as it was in the earlier data. So as a whole, it seems that the kind of the subsidence, the pattern of subsidence has migrated southwards from the city centre. So if we look at the previous data, the subsidence is here, here's the city centre, the subsidence is a bit closer to the city centre. And now it's moved to the south, and also increased up to the kind of west and the northwest of the city centre. So that's some kind of interesting observations. And then we just started looking at the relationship between the borehole data that we have. So there's a lot of groundwater abstraction in Hanoi because of the rapid urban expansion. And much of it is not documented or not officially documented. So we don't have a data set which is the complete picture of what's abstracted. So I'm just looking at the data that we do have here. And we see, you're kind of, the trends are the same. So here's the INSAR data plotted in the black and the red lines, and then the groundwater data, the groundwater level change is plotted in the blue lines. And one of the things that's interesting here is we're seeing the same overall trend. The ground is overall subsiding and the groundwater is overall decreasing over the same time period. But what we're not seeing is we're not seeing the kind of the details of the groundwater abstraction. The groundwater level change has been, fairly large. There's 15 meters worth, but we're not seeing that directly reflected in the INSAR data as we do in some other cases. So, here's an image that I've taken from a paper by some of our Spanish colleagues, and you can see that the INSAR data is tracking the change in the sorry, in the groundwater level change quite accurately, quite nicely. We don't see the same thing in Hanoi. So this just kind of made us think, well, is the groundwater level change the only factor at play here? Or is there something else that might be contributing to the subsidence that we're seeing? So some of the work that we were doing at the same time was this material flows work. So my colleague Alessandra was looking at the urban land cover change, so quantifying using satellite imagery, the urban land cover change, and then linking that to the amount of material that you would need to facilitate, so you need X tons of concrete and X tons of sand and cement to facilitate this urban expansion, and then trying to track where does that material come from and what are the implications of that. So as part of this, he processed, using Sentinel Landsat data, he just processed the urban land cover as a classification. And we can see the change of it here. So up in the top here, we've got 1996 urban land cover and then 2019 urban land cover. So the dark red pixels are the change, essentially, where we've got an increase in the land cover, the urban classes. And we just noticed that there was quite a nice correlation with the subsidence, some areas of subsidence in the INSAR data. So here's, INSAR data for the same area. And if we put over the land cover change, we see that some of that sits on top of it. Now, is that due to those, those new urban areas directly extracting groundwater, or is it something to do with the land cover itself and kind of the building processes that are taking place as they're doing it? So I went around the rest of the INSAR data and used the historical imagery within Google Earth Engine to kind of look at the change in land cover. So Google Earth's got great archive of historical imagery, so you can very easily go backwards and look, what was land cover in 2012, compare that to the INSAR data, and then 2014, 2018 in this particular area. And we just noticed some interesting land cover changes. So in this particular one, we've got quite a large area of subsidence up in the north here, a large spatial area, but also quite rapid rates of subsidence. And we can see in 2012, this industrial area didn't exist. And in the most recent imagery, 2020, we see there's a large industrial area. And we can see that gradually being developed 2014, 2018. And actually in the most recent data, you can see this little square of subsidence down in the southeast here, which doesn't exist. This image up at the top with the purple lines around it, it's just the base maps from ArcGIS. But we see in Google Earth, the more recent imagery, that there is, this development has continued along this road towards the east. And we see that that area of the most rapid subsidence in this particular area relates to that newest development. So is there a relationship between this development and the building of these buildings and the subsidence? So I then went back into the centre of Hanoi and looked at this area here, which has got the star on it. So here are our groundwater abstraction points again, and this area with the star is one of the most rapid areas of ground motion in the whole data set. You see the displacement time series for it here. And then I looked at the imagery once again. So here's 2016. So in 2016, we were starting to see it develop, but it's very wet. It's essentially a kind of like rice paddy fields, I think. And then over the months, this is gradually infilled with roads. And then in between the roads is infilled with aggregate. And then that starts to be vegetated. And then it gets buildings on top of it in 2020. So we're getting this kind of new land essentially being built. And it seems to be that this creation of the new land is loading the ground and causing or contributing to the subsidence that we see. And then there's a few examples where we start seeing it actually stabilizing once you get the buildings on there. And sometimes it can be very rapid, the stabilization. Once you get a new building, which has got piled foundations, we see the motion actually stops. So we can then go through the time series and we can relate these development phases to periods of motion. So when we get the initial loading, we see more rapid subsidence, and then we see that subsidence kind of tailing off as it starts to stabilize. So I then went through took me a while, went through Google Earth Engine for all the areas where we were seeing motion and just looked at areas which had significant development in this same kind of way between 2015, from 2008 onwards. So all of these black polygons represent areas which have rapidly developed from 2008 onwards and seen this ground loading in the same way. And then the purple polygons on the other side are just the dates of those. So we can kind of see that actually the areas which are undergoing the most rapid motion now tend to be the areas which were developed or loaded most recently, the darker purple polygons. So here's that in kind of detail for an area where, I've drawn the polygons around the areas of development, which has been interpreted from the image sequence in Google Earth, and put rough dates on it of when those were first developed, when they were first loaded with the aggregate, before the buildings were made, when the aggregate was first put there. And we can then look at the time series for all of those polygons and start to extract kind of rates of motion for each year after it's been loaded. So in this top one here, it was initially loaded in March 2018. We see in 2018 the most rapid period of motion, and then in the subsequent years, the motion starts to decline. Same 2016, 2017, we start seeing the motion, and it starts to decline. 2014, we're kind of capturing the end of the motion, and then it's stabilized after 2018. We can then start plotting all of that in, well, not plotting it all, so we can put it all into essentially a table for each year. So these are all the polygons that I've looked at. Each year, the year when it was initially loaded, and then the rates of motion for each subsequent year after it was loaded. So obviously 2008, we only capture the last couple of years because our data set's from 2015 onwards. 2019, we've only got the first couple of years because the data only goes up to 2020. So from this table, we can then plot an average subsidence rate for each year following the loading. So this is the average essentially of all of those lines in that table on the other side. So we get a rate of loading for each year following a rate of subsidence for each year following the loading. And the question then becomes, how relevant is this, and how much can we use this to help understand the development and the needs to kind of plan your development in the future. So just to jump to the conclusion, in Hanoi, the INSAR data reveals rapid rates of subsidence in the south and the southwest of Hanoi Centre. The centre is now stable. these areas of subsidence have kind of migrated away from the centre, and they've also migrated away from areas where we've got evidence of groundwater extraction. And there seems to be a nice spatial relationship between the areas of development and the loading, not due to the buildings, but due to the ground being loaded for the buildings, the ground being kind of reclaimed for the buildings. And we've been able to extract these expected rates of subsidence for each year following the loading. And now we're investigating how that can be used by the authorities for planning the development of the city. Okay, thank you very much.